Grigory.
Hi everyone, this is my third time in Armenia. I love your country, so I'm happy to be here. Thanks for inviting me. I'm CTO and co-founder of Intento. We are a startup that finished Berkeley Skydive program together with Crisp. So hi Crisp, you guys rock. I love what you do. And wider, I heavily impressed by what's happening in Armenia regarding AI. You have a lot of activities that I deeply respect everyone who's involved in it, so you're cool, really cool. So my talk is about transformers and what's happened with transformers in 2029. And as some prerequisite, I assume that you know what is transformer, but anyway, I'll give a very short 1 minute introduction, what is it, to help those who do not know what is transformer. Anyway, there are a lot of good information and materials on transformers. I give links to some of them here. Presentation will be available, so feel free to follow the links. And I put a lot of links in the presentation, so I will not try to read everything on the slide. It's designed to help you outside of this event to carefully follow what you are interested in. So, a very short recap. What is transformer? Transformer is a new type of neural network architecture emerged in 2017. It's a completely new architecture based on self-attention, a new mechanism. Actually, attention mechanism was before transformer, but transformer designed a new kind of neural networks based on the main unit of it that is called multi-head self-attention mechanism. Transformer is designed as an encoder-decoder architecture, and it's completely different from RNN or CNN. And it's good, better than RNN in terms of computational complexity, because training transformers typically perform much faster because all the operations are paralleled, and that's significantly better than the typical case with recurrent neural networks. And transformers produce good results on most of benchmarks. So some schemes on what's inside the transformer, and this is the heart, the core of transformer. It's multi-head self-attention mechanism. By multi-head, it means that there are several different, stacked attentions that stack together to produce a combined representation. And the deep core of this self-attention is this formula. It's softmax of two large matrices, Q and K, query and keys, and this thing produces weights for the incoming elements, marked here as V values. And that's the essence of transformer. Transformer looks at every element of the sequence that came to its input and weights it. And when you process every element, this element attends to other elements, and the weights of this attention calculated by this formula. And looking at this formula, you can see that it actually has quadratic complexity. This multiplication produces n squared complexity, and this limits most use cases for transformers, because for long sequences, it's very computational. It is very hard to produce meaningful results in normal time. It's mostly prohibitive from using it in real time. So transformers, vanilla transformers, has a lot of problems. It's pretty heavy model. It's not easy to train. There are tricky learning schedules with warm-ups, with cyclic learning rates, and so on. And n-squared computational complexity limits its scaling, and so it has limited context span. By context span, I mean the number of incoming elements transformer can attend to in a single run. And typically, this attention span is limited by, say, 512 tokens for BERT, or kind of near 2,000 tokens for GPT-3. There are a lot of movement into efficient transformers, and I talk about it a bit to process longer sequences. And the original transformer was focused on NLP tasks, and for other modalities like images, audio, and others, you need different implicit biases to be better suited for these particular tasks. So that's it for very short recap. I hope it at least help for those who didn't know about transformers at all. But anyway, feel free to follow the materials. Illustrated transformer is, I think, the best paper describing how it works. So learn about it. Transformer is an important direction. So what's happening in 2029? I focused several directions. One of them is still large transformers. It's not new direction. It's continuation of the old one. Efficient transformers, the same. They usually go together with large transformers. You cannot do large transformers without making them more efficient. And the new big thing is new modalities. Transformers came to images, audio, to biological data. That's important. And transformers became multimodal. That's even more important, I think. And with multimodality, some interesting artistic applications emerge, and I like it. I'll show you some examples. So let's start. Large transformers. That's not a new direction. Even BERT was pretty large for those time. It was hard to replicate that work unless you have good GPU machines and ability to run it for several days or weeks. And this picture was taken from a paper about stochastic parrots. I give a link and tell about it a bit more. You see that number of parameters in transformers grow significantly, and you know about GPT-3, the largest model was 175 billion parameters, and this is so large that it doesn't fit into any consumer, any GPU. You have to build your own cluster just to run this model, not even to train. And that's not a limit. There are some transformers which even larger. For example, switch transformer, it's built on completely different technology. GPT-3 was dense transformer, this one is sparse transformer, built on mixture of expert technology. That's good technology, I focus on it as well. It has 1.5 trillion parameters, it's really huge. And in this year we have a great deal of other new large transformers for language. We have English, Russian, Chinese, Korean versions. We have transformers for code. You definitely heard about OpenAI's Codex, and Google recently published their own paper with unnamed transformer for code. And all these models are really large. Google's one was 137 billion parameters, again, a huge model. And we have scaled versions of previously known transformers like XLMR or some variations of old T5 model, Byte 5. We have Deberta, we have switch transformer, we have Ernie by Chinese researchers, and so on. And most of these models are pretty large, and they're trained on really large, even huge data sets. And that scaling matters. There are some papers that focus the scaling laws of these transformers, and these papers highlight that the scale really improves the performance of transformers. The loss is better, everything is better, and the important thing I want to focus is that larger models require fewer samples to reach the same performance as smaller one. That's important thing, and that tells us something about the nature of transformers. I don't know, I'm not sure we deeply understand for now what does it really mean, but that's an important phenomenon, and we need more research into this direction because there lies something important for the field, for understanding the deep learning. And there are many benchmarks. One of them is a pretty well-known SuperGLUE NLP benchmark. And in this year, 3 models, all of them based on transformers, reached human performance, and now they are above the human performance. that's pretty impressive result because superglue was designed after glue benchmark was dominated by models above human baseline. So superglue was designed to be even harder, and just a couple of years after this happening, we see some models tend to dominate this harder benchmark, and probably that means we need some kind of superglue or hyperglue. I don't know that another benchmark, because in a year there will be much more models above the human baseline, so we need more tricky baselines. That's interesting phenomenon. And besides the good parts of large models, there are bad parts of large models. There are many problems. One of them is very obvious, the cost of training these large NLP models, because as an independent researcher, you typically have no option to train such models because it requires heavy investments in hardware, in data gathering, in training, in electricity. And costs for replicating these models range from tens of $100,000 to $1 million, and for most companies it's just impossible just to replicate this work. So it's important to have published models of this kind to be able to just use them. And in addition to larger money expenses, you have some other side effects, for example, carbon emissions, that's matter. You probably saw these numbers. It's a bit tricky numbers. Typically, the number at the bottom is communicated as a reference number, but it's not a good reference because that number was for network architecture search transformer. That's a really huge experiment with running, I don't know, hundreds or even thousands of very heavy transformers, and that's not a reference, not a good reference, because I don't know how much such experiments run in the world in each year. I bet not more than 10. And anyway, if you even run this experiment and build some new transformer based on this research, it's good because that transformer can benefit millions, even billions of people, and comparing to average lifetime of one car, that's not a really large number, just 4 cars. So I think it's good investment, even comparing these large carbon costs. But anyway, it's an important topic, and the world is more focused on it, and I saw there is in our program Stefan talk about sustainability, so it's important. We need to be careful and to invest our time and efforts in solving these problems. There are other interesting cases, for example, training data extraction from large transformers. It's related to data privacy and so on. You can, by designing some tricky prompts, get data from this trained model to understand. Sometimes you can extract some IDs, some links to maybe secret sites, some personal info, it was present in the training data, and that's the problem, and that problem became and will become more important because data gathering is pretty heavy and complex process, and it's hard to clear this data, to remove it from training data sets, and that definitely some data will be there, and some people can extract this data and find something personal, something they can use in a malicious way. And I think you know this paper, you heard of it. There was a lot of activities related to this paper. Some people were fired from Google. Tim and Grigory published, and with co-authors, published this paper on the danger of large models. They called it stochastic parrots. Do not try to read this slide, just here to highlight that there are a lot of problems. You can read it carefully in your spare time. And they called this model stochastic parrot because this model do not really understand what's inside the text. They just heavily use probabilistic information to build relationships and to give meaning results that look meaningful, but we know that these models make very stupid mistakes sometimes, and that signature of not really having the deep understanding of the world. Now these models are called foundation models, and in August, Stanford runs their own special center for research on foundation models, and by foundation models they mean models that trained on large data and the multimodal models, the models that has the potential to be adapted to very different use cases. And right now they're starting to investigate and do research around these models. And they published a paper more than 200 pages about the opportunities and risks of these models. So read it, at least look at it, because it's important to see a lot of different aspects that arise with these models. And I like the visual formula of total value for this model. It's not complete, I think, but anyway, I like it because it highlights the different aspects, good and bad, social benefits and environmental benefits. This model can benefit all of this, and we can use them for good, but also we can use them for bad, so we must prevent it somehow. It's a tricky question. And there are many costs like energy costs, social costs, second order effects, and so on and so on. So investigating these models is a tricky multidisciplinary question that needs attention from economists and other people as well. So that's it for large models. So we have a lot of large models just in this year, and we will definitely see much more larger models next year and the next one and so on, until we reach HI or something like this. And coupled with large models, there is a movement to efficient transformers. There is good paper, Efficient Transformers, a survey. They highlighted different aspects of improving transformer performance. You can add memory, you can add recurrence, you can change kernels to be linear or sparse or some other special kernels. There are many options to make transformers more efficient. We have had a paper with Mikhail Gurstov about memory transformer, so in this red circle as well. So you see complexity of transformers became better. There are a lot of linear transformers now, so it's easier to work with larger sequences, but we'll still have a lot of problems with this. The problem is not solved. We still have no good options to work with large text, with structured text, with hierarchy in it. It's still a problem to feed a large paper or large text into transformer and get meaningful summary from it, because even with linear transformers, the problem is not solved. And there are many architectural improvements and innovations in this field. I highlight just a few of them. There are much more beside my talk. Switch transformer built on the mixture of expert architecture. That's important not new, but that's important architecture that gained a lot of attention in last years. The idea is to replace some layers of transformer with what is called mixture of expert, as separate neural networks and which are called experts, and some routing networks that chooses which expert will process the particular token right now. Among, say, 100 or 1,000 of experts, a special neural router will choose one of them to process the particular item, and for next item, some other expert can be chosen. So this one transformer had 1.5 billion or trillion parameters. It's really, really huge. And there are many other mixture of expert improvements, for example, base layers, balanced assignment of expert layers from, I think it's from Facebook team. They're working in this field as well. And there are some other improvements like top K attention. It's the approach to replace the vanilla attention with a very accurate but fast approximation, and it produced good results. And another paper I really like is expire span transformer, because you probably heard of compressive transformer from DeepMind. It had two different types of memory. From the current span, the items moved to short-term memory. From short-term memory, they moved into long-term memory, and transformer work with this compressed data in memory. This transformer from Facebook team goes a step further. It allows not only to store items in compressed memory, it allows to have for particular item a different expire span. It allows the model to forget something, and it allows to forget items with different regularity. That's important thing. We as people, as humans, need to forget many things in order to be efficient and learn something new. So transformers become able to do similar things, and that's a good direction. I expect to see more such things in recent future, so keep an eye on it. And the most innovations in the field of transformer, I think, was concentrated into new modalities directions. And we already had a lot of transformer for images in previous years. So this is not a new direction as it, but just in the last couple of years there were a lot of new image transformers. I mentioned a few of them. There are much more. Again, a good survey of transformers in vision. You see there are many directions to change something in transformers. There are pure attention models. There are some mixed models that try to mix convolutions and attention. And one of the seminal papers in this field is vision transformer called VIT by Google. It's interesting because it's almost replicating the transformer for NLP. Here the image is split into patches, for example 16 by 16 pixels. These patches are then flattened just into an array of numbers, and then you learn linear embeddings for these patches, and then you work with image just the same way as you work with text tokens in BERT. You have the same CLS token like in BERT, and this transformer has almost the same architecture as typical text transformer, and it was designed for classification only. So you have a single NLP head on top of it, and it predicts the class of image. And what's good with this transformer, first of all, it's good that the text-based model works for images. That's interesting. Absolutely the same approach, works pretty good. And that model scales very well. This transformer was trained on a large data set. It was a huge transformer, and it gives very, very good results comparing for other convolution models on ImageNet and other data sets. There were improvements for this model. For example, data-efficient image transformer date almost the same as VIT, but it uses distillation, another technique I really like. If you don't know what is distillation, that's a very clever technique. You can take large model and you can train another model to replicate the behavior of this large model. You feed the same inputs to both models, and you try to predict in small model the activations of large models. And this small model could have the same performance, even sometimes better than the large one model. And again, that's an open question. Why does it work? And why does it work this way? But it works, and that's really interesting. There are some transformers, for example, bottleneck transformer that actually takes a ResNet, a residual network, and in ResNet you have ResNet blocks that take a higher dimension input compressed into a smaller dimension, then expanded back. And this middle part is replaced by multi-head self-attention, and it works. It gives good results again, so that works. And it's interesting because these transformers and these neural networks in general is really kind of Lego blocks. You know some blocks, you can combine it in different ways, you get meaningful results. So Lego for adults. You can build any different models for solving your tasks, and that's cool. And most of these blocks are available. You don't even have to program or train them from scratch. There are a lot of different models available to download, for example, in Hugging Face transformers or just in different neural network zoos. And again, mixture of expert model. There is a vision model. The idea is the same. Replace some block in transformer with block comprised of experts, and again to have a special module that chooses which expert to run. So this important technology will definitely see much more examples of using these type of networks. And even I think you've heard about FastMoe library built by Chinese researchers. It's designed to use Moe framework with PyTorch, and Chinese institutes, I think they built a really large models based on this technique. So you can take it and build your own large models, and it gives you some benefits. So that's a new type of scaling models. Before you can scale models by data parallelism or model parallelism. Right now you can scale models by expert parallelism. Just add more experts and the model gets better quality. For speech, again, we had a lot of transformers. Some of them were mixed convolutional and self-attention transformers. I like some new papers. For example, audio spectrogram transformers. You see that almost replicate it. You have input spectrogram presented as image. You split it into patches. Then you put it into linear projection. You have again the CLS token here, and that good old BERT architecture transformer encoder that can classify audio for now. Another similar model, audio caption transformer, the same encoder that tries to split spectrogram into pages and build linear projection for them and so on. Here, just text decoder is added on top of it, and you have a complete model for speech transcription. And another good model I like is multi-channel transformer. There are a lot of settings when you have several different audio channels. For example, in smart speakers, you typically have several microphones, or you have settings when you use several smartphones to record the meeting, and you can now mix these different channels into one single transformer, and it has a channel-wise self-attention or processing each channel separately, and it has cross-channel attention to mix all these channels together and produce results. So that's good direction, but again, the blocks are mostly the same. You just build a new architecture how to combine these blocks and get something new and with better quality. And the topic or modality I really like is transformers in biology. You definitely heard about AlphaFold 2 this year, last year. DeepMind built a really good model that won on CASP competition on predicting protein structures, and it looks like it was an imagine moment in biology because the distance from the leader to other participants of this competition was really huge. The AlphaFold was a completely new model that was significantly above any other. And what's interesting, there are many transformers for biology. For example, ESM1B model, protein language model. You can use proteins. Proteins are represented as a sequence of amino acids, and you can treat the problem of predicting what letter, what protein, what amino acids should be in particular position, the same way as you work with NLP models. And I think there are people from Facebook AI, they built this model and they trained it the same way you train BERT to predict masked tokens, masked amino acids, and suddenly this model has interesting properties. You can predict even, you can fine-tune this model later to predict contacts between parts of this protein. That's useful medical and biology tasks, and that has value. And there are some other models. For example, Rosetta Fold was an approach to replicate AlphaFold 2 system before AlphaFold paper was published. And you see it's pretty complex. It has very complex structure. You have several paths in this model, 1D track, 2D track, 3D track. And each track has its own separate attention modules. Some use that is called Excel attention, a special attention variant for working with images or multidimensional data. And some parts of this model use graph transformers. For example, SE3 transformer is a graph transformer, and graph transformers are a separate important direction in this field. There are many graph transformers. Graph neural networks is another emerging type of networks that has much value in different cases. So it was used here, and they were used in AlphaFold 2 model. They built a special block called EvaFormer, and it uses multiple signals alignment, a pretty unique type of data that exists only in biology. It incorporates evolutionary relationships between different sequences, protein sequences or DNA sequences. And as Dobzhansky said, nothing in biology makes sense except in the light of evolution. So evolutionary signal is very important type of signal. Only biology have right now. But it's interesting, actually, maybe someone once built some kind of evolutionary transformer for NLP, because languages has the same behavior. There are evolution relationships between different languages. So I didn't see any works that try to build NLP models this way, but maybe some of you or other people will build some kind of transformers for NLP with evolutionary signal. I think that's interesting direction. And the most fun part is multimodal transformers. Obviously, you don't have to build transformers designed on only a single modality, speech, text, images, and so on. You can mix them. And there are many different options how to mix. You can mix different modalities earlier in the pipeline, or you can mix them later, and you can mix different modalities. And some important examples are DALL-E by OpenAI. It's beautiful because it's pretty simple structure. I mean, you take images, you build a separate model called discrete operational autoencoder, just to replace the image by smaller amount of image tokens that are learned here. And then you take these tokens and you build a GPT-3-like model. You put these tokens into input. You can add some text. That's vice versa. You put text tokens, then you put image tokens. You can put some starting of image, or you can put no image tokens at all, and the model auto-regressively generates image token and produce image. So this model was trained on pairs of images and text on very large data sets, and suddenly it shows pretty impressive behavior. It can produce image objects that never existed, that definitely not existed in the training data set, so it has some generalization. So we can produce a tapir made of accordion, and it looks meaningful. It makes mistakes. The right image is beautiful. An illustration of baby hedgehog with a Christmas sweater walking a dog, and some images with no dogs, but another hedgehog. But it's good. That's mistake, but some of these mistakes resemble mistakes children make when learning to read complex texts. So I like these examples because these mistakes are pretty close to our own mistakes. So that's that means something. The embeddings should be close. For other objects, they should be far apart. And training model this way, you can have a good embedding space, a single embedding space for text and images, and then you can use it in different ways. In DALL-E, they used it to rank the several candidates. DALL-E produced several images, and then they used Clip to understand which image is best suited for this particular text that was put as prompt. And they filtered, and it works. It filtered really good examples, and some better not used. For example, DALL-E can produce 50 images, and Clip just choose the best one. And the results are good, and contrastive learning is the interesting field, and self-supervised learning in general, again, is a very important and productive field. And I know tomorrow Michal Balko will talk about Bootstrap Your Own Latent paper. It's one of the seminal papers in the field, so I heavily recommend to visit it because I like this paper. It's really cool and important. Google has the same type of model. It's called Align. Again, they trained a similar type of models, multimodal models of text and image pairs. The only difference, they trained the model on a noisy data set. They do not heavily invest in filtering the data set. They just gather a much larger data set, and suddenly the result is even better than Clip with smaller but heavily curated data set. So that's an interesting model. Somehow learns how to distinguish, how to deal with noise. It can extract some meaningful signal from there. So that's important. Scaling works in this way too. And one of application of Clip is artistic application. I like it. Maybe you remember Deep the Rim. That was a technique in the early times of this wave of deep learning technology. You can optimize the incoming image to maximize some activation in the network, and image is changed in a way so the neural network thinks that some kind of object is there in that image. You can use this approach here with Clip, and it's cool. You can this particular work uses a differentiable rendering. You can put, say, 1000 Bezier curves on the image. Then you have differential rendering that, not on the image, just put 1000 Bezier curves on the canvas. Then you can render it into an image. Then you can feed this image into Clip model. From another stream, you can feed the text you want to generate image for. And using gradient descent, you can change the parameters of Bezier curves to produce image that reflect this text. And some cases are really good. This image was generated for this prompt, beautiful epic one-cross fantasy painting of the ocean. It consists of a lot of Bezier curves, and the result is pretty good. I like it. So you remember when artistic style transfer and the paper of Leon Gattis was published, a lot of different applications emerged, Prism, for example. And I think this type of models open the new universe of possible applications for generating images based on text. And that's one good example. Another good example is using Clip with the same differential rendering, but now instead of Bezier curves, you use pixels or squares, and you optimize the image the same way, and you have such kind of 8-bit images reflecting the text. I like it. It's really cool. It's beautiful. I don't know which product we can build with it, but we definitely can build something. And I suspect people from Pixar already know about it and maybe go in this direction. But anyway, that's definitely a place for some new product with this technology, and that's just one example of using this type of foundation models in new unpredictable ways. Artistic creation of content. So good example. it's just emerged in this year and already have beautiful results. And another interesting work from Google, actually from DeepMind, is Perceiver. They positioned this model as a general architecture for multimodal embeddings. And the idea beside it is pretty simple. You can take any inputs of any size, and you use a special type of attention called cross-attention. You add latents to the model, latents array, some latents, low-dimensional latents, and these latents attend to a specific part of the input sequence. And attention mechanism could decide which part of input to attend. And this model originally was used for classification, and you can attend to completely different modalities. You even can mix different modalities. You can attend to audio signal, to images, to text, and mix all this signal into latents, and then produce some classification, for example. And in addition, for free, you have much lower computational complexity because latents are typically small, and the n-squared complexity removes from the equation here. You have linear transformer in this way. And recently, DeepMind published improved version of Perceiver. It's called Perceiver IO. The problem with Perceiver was it was used for classification. It could produce a single item. And if you want to, say, convert text to image or image to image, you need different outputs. And for Perceiver, they solved it by adding an output query array. This is a learned queries for particular data types. And all the networking is the same, but on the output you use these output queries as a query for these latents, and for each query you produce a single result. For example, a pixel could be a query, and you can produce an image on the output. So this model works. It works good on really hard and complex tasks, and that's a good model to build some multimodal solutions for mixing different modalities. So look at it. It's very recent. It's just 2 months old, and the code is published using modern JAX framework. If you don't use JAX, look at it. JAX is really cool. Kind of NumPy with AutoDiff on steroids from Google Brain team. It could be a good alternative for PyTorch, and many researchers already use it. So that's basically it. I only scratched the surface of recent transformer models. You see that there are a lot of different transformers. You see there are a lot of movement into multimodalities and into new different modalities. So if you have a question, I'm ready to answer. So thanks for your attention and self-attention.
Thank you. Can you hear me? No. Who has questions? Make this work. Yeah, but we need to find a good microphone. Let's try this one. Hey. No, doesn't work. Someone can fix this. Okay, let's try.
You can ask from here. I repeat it.
So first of all, thanks for a great presentation, Grigory. And my question is the following. Since it is for me your opinion, do you see any new types of neural network architectures completely different from transformers, which has a potential to overcome transformer-like architecture? For example, several years ago, LSTM-like neural networks were the mainstream, and then they were started by transformers. So I'd like to hear your opinion.
Yeah, that's a good question. It's hard to predict future. It's easy to predict past. We don't know. definitely some architectures emerge. I don't know which particular architecture will emerge, but someone will definitely. I think some recurrent neural networks is underestimated still, and there are many different recurrent neural networks models, very complex one that has good potential. For example, Mogrifier LSTM is very tricky LSTM which still produce good results, even comparing with transformers. And there are many different recurrent neural network architectures that tries to have biology and neuroscience inspiration, and there are many such works. And one kind of works I personally like and watch for is hypernetworks. These are networks that actually contain two types of network. One network generates weights for another networks. And I like this idea. It's pretty interesting, and I believe somehow someone could train hypernetworks to completely new tasks and completely new architectures as well. So that's one candidate. Maybe there are other candidates. Energy-based model gaining attention for now. Graph models taking attention. We'll see.
Thanks.
Maybe we have time for one more question. I wanted to ask one. Okay, so as far as I understand, these visual transformers are trying to do everything to avoid convolutions, right?
Yeah.
But then if you look at the first layer, what they do, it's like a convolution with one filter and stride 16, right? So what's the point? Like maybe we can just have one layer of convolution and then start the attentions. What do you think about that?
Actually, attentions are not very far from convolution, and these are pretty related models, but and at least you can replicate convolution model with attention and vice versa. Just build more convolution to have more context, and you build almost the attention models. But attention is interesting in terms of it has lower amount of implicit biases compared to convolution. With convolutions, you try to build models with your own understanding of how these models are built in biology, for example, how visual systems are organized in living organisms. And that's good. You incorporate your domain knowledge, your implicit biases, and have good performance with smaller number of parameters because you invest in the good structure. But that structure is good for images, and maybe it's not good for other type of images. Because again, our visual systems was trained by evolution in the long term to work with world around us. But for completely different visual worlds, maybe some other types of implicit biases are required. And for other data types, definitely other types of implicit biases are required. In these terms, self-attention and transformers are good. They can learn these biases. They have a smaller number of constraints for this, and you just need more data. That's a trade-off. You can invest into good biases or into more data to find this structure in the data. So that's a spectrum, not two poles.
Thank you. So let's thank the speaker again.